So just some other graphs. One of the other things they like to do is write y equals some other known function, and they change it. So you might have y equals function x, but they might say, hey, draw the cosine of function x, or the sine of function x, or e to the power of function x, that sort of thing. So I thought I'd just look at a couple here that have appeared back in the past. So here's the original graph they gave in 2003. The first one they asked that year was the good old standard, let's draw the reciprocal. Okay, so the key things for our reciprocals, we know our vertical asymptotes become x-intercepts, sort of. The first thing I did is I located where one is. Now I'll put those x-intercepts in, there they are. But remember, they are point discontinuities. They've given me where 2 is, so we can use that scale to work out roughly where 1 is, because when you turn 1 upside down, you get 1. That makes a nice one. Now in this case, it's going to be underneath, because when I turn -1 upside down, I'll get -1. And my turning point there at 2, when I turn 2 upside down, I'll get as half. Alright. Now, so we know it's going to go through these point discontinuities. They're going to look like x-intercepts. It's going to go through the red dots. So all we really end up with is an upside down U shape, a bit like a parabola, although that one doesn't look much like a parabola, but that sort of thing. Okay. The next one they asked was function x plus the absolute value of function x. So first thing I've got to work out is what is the absolute value of function x, and then I'm going to add the two graphs together. So absolute value of function x, whatever is below gets reflected above. So my blue graph there is absolute value of function x, and I'm going to add the two together. So obviously this U shape, it's just going to be twice the y values of every single point on that U. So we'll just draw that there. Okay, so we double 2 and we get 4, and there's our U shape in there. Now, the big mistake a lot of people made with this was to go, oh, the bit below and the bit above cancel each other out, and just didn't put anything in. But of course they add together to give 0, so you would actually have a line there. And the point is, it would stop at that point there. Well, how many of you were thinking, yeah, I wouldn't draw anything there? Yeah. Right, function x squared. Function x squared. Now, we haven't got any x-intercepts on this one, so what can we do? Well, square 2 and you get... So again, in between those two asymptotes, we get a U shape. Now, these end ones, well, when I square them, they become positive, but I'm just going to bend towards these asymptotes. Not a really interesting graph, that one, but there's function x squared. E to the power of function x. So when I do these ones, to the side, I like to draw the basic curve of what we're trying to do here, and that's e to the power of x. So that's y equals e to the power of x. Now what we're going to draw is e to the power of function x. So the y values of this basic curve that we're starting with are going to be the power. So it'll be e to the power of that. So we're going to look for important points. So what's probably the most important point with an exponential there? Which one? 1, the y-intercept. Now how do we get the y-intercept? It's when it's e to the power of e to the power of 0. So we want to have a look at our original graph and ask, when is it equal to 0? Well, when is it equal to 0? Never. However, we do have a horizontal asymptote approaching 0. So therefore, my new graph will have a horizontal asymptote approaching e to the power of 0 or 1. Okay. So I know that. Other things you can do. You can have a look at the derivative. You might like to investigate that to get a feel for when's the curve increasing and decreasing. And we can see, look, the derivative is times the derivative of the old graph. So I know that turning point there is still going to be a stationary point. So I know that's going to be true. Stationary points remain. So let's plot some points in. So it's e to the power of the y value. So this time the y-intercept becomes e to the power of 2. So e squared. It's then going to go up like the exponential. Because if you have a look over at our basic one that we drew over here, once we went with 2, what's the exponential curve doing? It's going up into that concave up shape. Well, we're substituting in numbers bigger and bigger and bigger and bigger and bigger. So it's starting to look like the exponential in there. So there's the U shape. What's happening out of the right hand side? There will be point discontinuities at the x-axis. And there's that horizontal asymptote I was talking about before. What else can you tell me about the curve? Positive or negative? Got to be positive, because our exponential is always positive. So I've got to get from that point discontinuity there. How did I know that was a point discontinuity? Well, the y value of the original graph is approaching negative infinity. Have a look at your exponential graph. As it's approaching negative infinity, it's getting closer and closer to the x-axis, or closer and closer to 0. So I knew I had a point discontinuity there. I really have one decision to make. So in other words, is there a point of inflection in there? Now, how can I tell the difference? Well, the difference again comes down to the first derivative. Have a look at the slope near that point discontinuity. If it is the first one, which most people probably would assume it is, most people would just go bend towards the asymptote, then the slope of that is well, certainly greater than 0. It's got some slope to it. Whereas the second one, where we inflect and come in flat, that's the one that's going to approach a slope of 0. So what's our derivative doing? Our derivative is the derivative times e to the function x. When we multiply two things together, which one of those will dominate? Exponentials will always dominate. So what is e to the function x doing? Well, e to the function x would be approaching 0. Well, because e to the function x is the y value. It's 0. So in other words, the derivative is approaching the value of the exponential. So it's actually going to get closer and closer to 0. So it's coming in flat, and that's how we know it's got that inflection point in there. Very tricky. Why is there? Because I know it's got to bend towards the asymptote. But what I'm saying is, when it comes into that point discontinuity, it comes in concave up, because it's flat at the base. It's not coming out of it concave down. If it was coming into the point of discontinuity concave down, then it wouldn't have an inflection point. It would just go like the top one I drew there. How did I tell? We're saying it's equal to f dash x times e to the function x. And so we're either saying, hey, is that approaching 0? Because that's what f dash x would be around there. Or has it got some size to it? Okay. So, e to the function x, well, that is this graph. We know at that point, e to the function x is approaching 0. So that part is approaching 0. The derivative is approaching minus infinity. But the question is, when you multiply, which one of those two is going to dominate? And the exponential will dominate. So therefore it's going to go towards the 0, not the minus infinity. Let's have a look at another one. So here's the 2002, the graphs they asked us to draw. The first one was the reciprocal, again, and it's sort of one they asked us to draw. So the x-intercepts will become vertical asymptotes, We have no vertical asymptotes to go the other way. 1, when we turn upside down, will be 1. Minus 1 will be minus 1. Let's plot those in. There's minus 1. Positive 1. Remember the other idea? Whenever the original graph was increasing, the new graph will be decreasing. Things like that. So we end up with... that's what I was saying. So above and below 1. There we go. There's our red graph. Y squared equals function x. This is the one I was talking about. Had the potential to be a fantastic question, except for when you find y squared equals function x, that's what do we draw first? Y equals the square root. Now, when we do the square root graph, what's the first thing we do? Anything that's below disappears. So we're just drawing the square root of that. But that's the thing a lot of people forgot about. Because when you rubbed it out, that point at 0 still existed. So there is a dot at 0, and then over there, well, I made mine just do it like a parabola there. That's y equals the square root of function x. We want plus or minus. It's a beautiful vertical tangent, I'm sure you'll agree. It's an excellent graph. Alright, absolute value of function absolute value x. So what happened with absolute value function absolute value x? First thing we did was draw function absolute value x. And function absolute value x was whatever's on the left disappeared, whatever is on the right hand side reflects over. So that's function absolute value x. But we're now going to do the absolute value of that. So whatever is below will reflect above. And there's our... Honest, that's a nice neat point there. Trust me. That's absolute value function, absolute value x. The log of function x. So again, I'll just draw a log curve here. There's y equals log x. But we're going to draw y equals the log of function x. So the log of all these y values. What do we know about our log curve? Cannot find the log of a negative number. So again, and this time that dot will disappear as well because you can't find the log of 0. Now, at 0 on our log curve, we have a vertical asymptote. The log of 1 is 0, so that will become the x-intercept. And basically then, I'm just going to have the log curve because I'm substituting in all of the numbers going from 0 off to infinity. So it just looks like a log curve, really.